Hello there. Today we'll be doing the problem called perfect squares. Write a program that determines the smallest number of square numbers that sum up to n. So in this particular problem, we can see that the greedy approach, trying to use the largest number, will not work. Suppose that we have 18, example 18. If we try the biggest item, which is 16, we would need 3, because we need a 16, a 1, and a 1 to get 18. Otherwise, we can do it with 2 3s, so 2 item output. So we would get the wrong answer. So the greedy approach does not work. What we need to do is to build up this solution. We want to know if we can, how do we build up the solution? So as you can see here, we see a 16 plus 1, we see a 9 plus 9, we see a 1, right? So let's see how many times do we need to build up a 9, right? If we can build up a 9 in one step, right? And we find out that using a second 9, we could get 2 output. Then we can get 18. So instead of solving for 18, we solve it by using subproblems of looking at 9 to solve it. Okay, so what does that mean? So what that means is, let's say we have a tree, this tree, right? Let's say we have a 4. Well, what we can do if we're 4 is that, let me see, I think it's like that and that. Okay, so there's a decision tree here. What we can do is we can use a 1, we can use a square, other square is 4. If we follow this decision tree, we can only use another 1. We can build up to the 2, and then build up to a 3. So to use a 3, we would need 3 times, 3 ones. To build up a 4, you only need a 1. By getting this minimum and building this up, we can find out for every total, if we use a particular square, how many ways is there to get another square. So let's say for 18, we have the possibility is 4, 9, and 16, right? So what happens here is that we have many more possibilities of what we can do. And from a 9, we can build up to a we just need to solve the problem of getting 18 minus 9. In this problem, we have to have 18 minus 4. And this is 18 minus 1, which is 17. And this is 18 minus 16, which is the subproblem 2. So the problem that we need to solve here is 17. The problem we need to solve here is 14. Number we have to solve here for is 9. And the problem we have to solve for is 2. And suppose that we have all of these numbers already. Then we know that it will take a minimum of two items to get to 18, because we have a 9 and a 9. and it takes 1 to get to a 9. So we can say that, well, we only need a 1 item here and another item here, and we can get a total of 18. So how do we do this? So let's build up the dynamic program and find out. So first of all, we set the dynamic programming to equal to all the targets possible. Then we set the first item to 0 because that's our base case. It takes the 0 items to build a 0. So if we're gonna build up each target right now. So each target in range of 1, n plus 1, and for each square in the target, we need to go target plus 1 to get to the target. And square is equal to s square times square. Then if our target minus the square is under 0, that means we no longer need to check anymore. We just break. So we're going to set the target equal to the minimum of the current target, 1 plus the dynamic programming problem of the target minus the square. So we look at how long it took to get the previous number. We're going to use 1 more square to get there, to get this current square, to get to that previous square. And now we're going to return the dp of our target, which is n. And you can see that, right. You can see that this works, right? Okay, so I think we should run through an example here on how this works. So let's try 18. So we're gonna build up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We're gonna build up all of these targets to get to 18. You might ask, oh my god, that's a lot of processing, but that's what we have to do. So we set the first one to 0. Then we check the target for 1. How long does it take to make 1? Well, it takes 1 squared target, which is 1, minus 1, it takes 1 time. 2, it takes 2 time because, well, if we build up the 1, we take the 2 minus the square of 1, it's going to be 1 plus 1, so it's 2. For 3 is that we're going to take the dp of the target, 3, minus square, which is 1, and that's going to be 2. 1 plus 2 is 3. Now we do the 4. 4 goes in, which is tries the first target, which is 1. Target is going to be the 4. 4 minus 1 is 3. 3 plus 1 is 4. So it's currently at 4. But then we do it again, and we do the square. We try the next square, which is going to be 2. 2 squared is going to be 4, 4, 4, minus 4 is going to be 0. And we look at the 0 spot, and we add 1 because we need to make a square. So it's going to cost us 1 time. And of course, we're going to keep building this up. This is going to be 2. This is going to be 3. Why is this 2 and this is 3? It's because 5 is going to try the 1. So if it tries 1 plus the previous item, which is a 4, well, it's going to cost 2 items. 2 items to get to 5. And then it tries 4, and 4 minus is also 1. 1 plus 1 is you know, that's how it works. So 3, and then 7 is going to be 4, because we go back to 4, and how many times does it take to get back to 3? It's going to be 3, so it takes 4 times. This is going to take 2 times. Why 2 times? Because we're going to do a target, which is 8, minus the square, which is going to be 4, and that's going to be 1. 1 plus 1 is equal to 2, and it's going to take 2 items to get to 8. 9 is going to be 1, and so on and so forth. 2, and then 3, and then this is going to scroll back. It's going to take a 3 because we go back to 8. It took 2 before. Of course, we're going to try 9. So the target minus 9 is going to be 3, right? So we look at 3. It's going to take a 3 plus 1, which is going to be 4, and we're not going to do that. And so 13 is going to be 4, 14 is going to be 5, 15 is going to be 6, 16 is going to be 1, and 17 is going to be 2, and 18 is going to be either 3 or is it going to be 2? So let's do 18 now that we've built up this entire dynamic program. So we try 1. And 1 plus 17 is going to be 3. It's currently 3. Then we try 2. Well, suppose we did 2. We added 4. We tried a 4. So we go back 4, which is going to be at 14. And it will take us 6 items. No, we're not going to do that. Then we try 9. Try a 9. We go back to 9. Oh, we took 1 more item, so it's a 2. And then we try 4, which is 16, and 16 is going to be 1 to get to 16. No, it's going to try 2, which is 16 is going to get us to 2, and 2 is going to be 2 more items, so it's going to be 3. And so 2 is the smallest item, so we return 2. And that's how we solve this problem. It's about building up our solution by using our previous solutions, which is dynamic programming. Right. So to do this problem, to figure out this problem, we need to see the common subproblems and how are we going to build this up. To see the common subproblems, we need to build the tree. If we build the tree like we did earlier, we will see that we will see similar problems prop up, and we want to solve for that particular problem. If we can solve for that particular problem, then we have our solution. So when you see when you have this problem, you try to build it out, and you see subproblems, then we can build up to our current problem, which is 18, our target. So the runtime is going to be we're gonna run n O of n first, because we're gonna go run it up to the target, and every time we build up to a square, we're going to build up all the numbers that square into 18, which is the square root of the target. So it's going to be n times the square root of n. That's our runtime, and the space complexity is going to be n because we use a dynamic programming to hold all the digits that we need to build up our answer to 18. Otherwise, we will be doing a lot of extra work to solve this problem, because we'll be doing a recursive solution where we'll have to solve the same problem many times. Anyways, that's the end of this video. If you have any questions, please comment in the comment section below. See how I can better explain this problem. And if you like this video, please like and subscribe. And if you want more material, check out the link in the description below. Thank you very much, and have a good one.